Hello, welcome back to Piers Rocks. Last time I introduced the Software Defined Retro ROM. This time we're going to dive into some of the technical details. So first of all, I'm going to cover the requirements that I set on the project from the start. That then leads into the constraints that I was working with. We'll then move on to microcontroller selection, PCB layout and routing, and then some of the software challenges that I faced and how I overcame them. If you're interested in a particular element of that, there'll be sections down below, so please feel free to skip forward and backwards to the bit that you find most interesting. We're going to start though with looking at the datasheet for the original 2364 ROM. Here's the timing diagram and values from the 2364 datasheet. This tells you what you have to do if you want to replace the existing 2364 ROM. Now this is from a 450 nanosecond access time ROM. I don't know what value the 2364 ROMs in, say, the C64 are. They're either 450 or 350 nanoseconds. I'm fairly sure that the character ROM in the C64 is a 350 nanosecond part. What does that mean? If you look down at the timing diagram, then there are three different sorts of interesting pins that are shown. The first ones are the address inputs. The second one are the chip select input or inputs. You have one input on the 2364, more on the other chips. And then you have the data outputs. And what the ROM is supposed to do is read the address of the byte that's required from the address lines, and then when the chip select line goes active, which is normally on the 2364 going low, it has to set the data pins to output mode and have them actually transmitting the values of the byte that's been requested. So the value of the data byte at the address that the address pins indicated. What the timing diagram shows us is how long the ROM has to do that activity. And to actually get data on the data pins, there are two interesting timing values. The first one is from this point here, which is when the address inputs go valid, to when the ROM chip actually has to get valid data on the data pins. And that's TAC, which is this 450 millisecond access time. The second interesting timing is the chip select line, and you'll see that we have less time, TCO, from the chip select line going active to the ROM needing to get the data pins active. And TCO is 200 nanoseconds on this chip, and I think it's also 200 nanoseconds on the 350 nanosecond access time chip. So what that suggests is that the ROM chip is constantly keeping an eye, as it were, on the address inputs and figuring out what byte is at that address input and applying that to the data pins, but not setting the data pins to the output. It only sets the data pins to outputs once it notices the chip select line going active. So these are the key timings that we have to replicate on our replacement ROM: 450 nanoseconds or 350 nanoseconds, maximum amount of time from address pins showing a particular value to getting the data byte out, and 200 nanoseconds from the chip select line going active to actually getting the data bytes active. Now, when I first reviewed this data sheet, what I assumed this meant was that this period here would be 250 nanoseconds, which is 450 minus 200. That's not necessarily the case. All this datasheet is saying is the ROM may take up to 450 nanoseconds to get the data valid from the address pins having a particular value on them, and it will also take a maximum of 200 nanoseconds to actually get those data pins to output having the valid value on them. So at least my reading the datasheet, and feel free to comment down in the comments if you think I'm wrong, I'm sure you would anyway, is that you do get both of those different timings if you're replicating this ROM. You get 450 nanoseconds or 350 from address inputs giving a value to getting the data byte out, and 200 nanoseconds for the chip select line. That's what we're working with. But just to put these timings into some sort of context, if you're using a microcontroller to implement this ROM and it's running at 100 megahertz, you get 10 nanoseconds per clock cycle. So that gives you 20 clock cycles for the chip select delay. And that might sound like quite a lot until you realize things like a single instruction may take 1 cycle, 2 cycles, 3 cycles or more cycles, you may hit flash wait states, which cause your CPU to pause for a number of clock cycles before it can read a particular value, instruction or data from the flash. So actually 20 clock cycles is not very much at all. Here are the requirements that I set myself on the project, and this is obviously reconstructing after the fact. They weren't as clearly in my mind, but I did have thoughts like this going around my head when I kicked off the project. The first and most important requirement I had was I wanted a single hardware variant that would support all of the 2364, 2332 and 2316 ROMs and all of the different possible mass programmed chip select behaviors. So that means 13 different hardware variants from a single board. The second requirement I had was I wanted it to be the same footprint as the original ROM. Wasn't really a particularly good reason for this, because I've never hit a problem with the larger alternatives actually hitting and fouling other components. But aesthetically, I wanted a solution that was the right size. Thirdly, I wanted all of the components on this board to be hand solderable. And look, yeah, I know this is absolutely subjective. What's hand solderable for one person is not necessarily hand solderable for another. These are all surface mount parts, quad flat pack 64-pin STM processor and 0603 passives. For me, they're solderable. For other people, they won't be solderable. If you want to get really good at surface mount soldering, and I'm not saying I'm really good at it, I would highly recommend watching some of Lewis Rossman's early board repair videos. That's kind of where I got the bug for doing surface mount soldering from, and where I learned a lot of my techniques from. So I'm as ham-fisted as he is. And then lastly, I wanted something that was cheap. Originally, I wanted to use a microcontroller on here that was $1 or sub $1, like the STM32F4 which some of the Chinese clones of you can get for under $1. As it turned out, that wasn't to be. So in terms of constraints on the project, those requirements led to, first of all, I knew this was going to be a software project. That's what I had in mind from day one. And I knew that was the only way to get the kind of configurability of chip select line behavior that I was looking for. Yes, I could have gone with FPGAs, but I know nothing about FPGAs. I'm a software guy, so this felt very much in my wheelhouse. Secondly, I knew that I was going to be able to get away with very few onboard components because the form factor of this thing is just so low, particularly because I wanted everything to be a minimum size and hand solderable. Thirdly, and this was probably the most limiting constraint, I decided to go with a microcontroller that had 5-volt tolerant GPIOs. Yes, you can get plenty of microcontrollers that could have done this job, but very few of them have 5-volt tolerant GPIOs, and the right number of them and the right locations of them. We'll come on to talk about that in a lot more detail later. The only way I could have used a non-5-volt tolerant microcontroller would be by putting components on the other side, which I've already talked about. I wanted to avoid putting anything on the underside. I wanted to keep it to a single layer component design. Then I knew that whatever processor I went for was going to need a really fast clock speed, and some very early prototyping with the STM32F4 Jelly Bean part really cheap led me to believe that that processor's maximum clock speed from the internal oscillator to keep component count low is around about 67, 68 megahertz, and I knew that that just simply wasn't going to be fast enough for this application. I wanted to keep it to a 2-layer PCB to keep the manufacturing cost low. That led to some significant trace routing challenges. And then I've already talked about the fact that I wanted to keep everything a minimum size on here so it was hand solderable, at least by me. Let's talk a bit about microcontroller selection. And I spent a lot of time agonizing over this. And here on the screen you can see the main variants of microcontrollers that I explored for this project. And it really was the 3.3 volt tolerant GPIOs versus 5 volt tolerant GPIOs that led to me where I ended up, which was the STM32F4 series of micros. Just to go through and talk a little bit about each of these, I really wanted the Pico to work, the RP2040 or the RP2350 to work, because they're super powerful, right? They've got dual core, they have base clock speed of 125 or 150 megahertz. They have the PIOs in them, which I reckon I could do some really funky stuff with. But they don't have 5-volt tolerant GPIOs, and you need at least 22 pins for this application for all your address lines, your data lines, and your chip select lines. And that would have meant 3 8-port level shifters on the circuit board, and I really didn't think I could justify that. And to fit it in the same form factor, I figured I was probably going to have to go for a 4-layer PCB, which I really wanted to avoid for cost and complexity reasons. So with a heavy heart, I discounted the Pico MCU. I very briefly considered the ESP32, but I didn't want something that was natively Wi-Fi on board this. And the ESP32 also doesn't have 5-volt tolerant GPIOs. Yes, I know the CEO of Espressive at one point said that you could put 5 volts into the GPIOs if you wanted to, and the micro wouldn't break. But he also said, why would you? I'm looking for something I can run in spec, so that put the ESP32 out. The ATMEGA does have 5-volt tolerant GPIOs, but they tend to be very low power, low clock speed processors, and I find them quite expensive to get hold of as well, so I dismissed that fairly quickly. And then the PIC, I didn't spend very much time looking at the PIC, but again, it looked quite low powered for this application and for the cost I was going to pay for those processors. So I ended up looking at the STM32 processors. Initially, I focused very much on the STM32F1, as I said before, because it's a much cheaper part. You can get them in onesie twosies from AliExpress for under $1, particularly if you're prepared to go with the Chinese clone variants. But it just doesn't have enough horsepower for this application. That's partly because the clock speed is a little bit too low. Again, I wanted to run this from the internal oscillator. That was actually another consideration I had with all the micros. Could they run with an internal oscillator and internal flash? Pico, yes, internal oscillator, no internal flash, except for some of the very new RP2350 variants. The ESP32, you need external flash, or you need quite a large module to use, and so on. Anyway, back to the STM32F1. Relatively low clock speed. It's also an earlier ARM Cortex processor than the STM32F4, and it has much worse instruction prefetching and caching, which influences how fast the processor can actually get the instructions in from flash, and that influences how fast and how deterministically the code will run. And again, some early prototyping suggested that it just wasn't going to be viable on the STM32F1. And then really importantly, the STM32F1 has actually quite a poor selection of 5-volt tolerant GPIOs for this application. It has enough if you go with the 64-pin variant, which is what I've gone with for the STM32F4, but they're not in the right locations. And I'll explain that a bit more when we start looking at the schematic. So I settled on the STM32F4, and this comes in processors with maximum clock speeds all the way from 84 up to 180. It has really good instruction prefetching and caching for this application, which is quite simple. I found no wait states being introduced from flash whatsoever, and its 5-volt tolerant GPIO support is really good, really optimal for this application. So let's take a look at the schematics next and look at that optimal GPIO location. So here's the schematic for the STM32F1 variant, which doesn't work, and I'll explain to you why it doesn't work. On the left-hand side, you have the footprint of the 2364, or the ROM that we're emulating. The right-hand side has the footprint for the microcontroller. And I have marked all of the 5-volt tolerant pins _FT. So we have 8 of them on port A, 13 of them on port B, and then a bunch more of them, 7 I think, on port C. Now, ports in the STM32 world are very important. You can access all of the GPIOs for a single port, a 16-bit port, with a single register read or write. That's important for performance reasons, that you have all of the pins that you want to use for a particular operation on a single port. So you only have that single instruction that you need to execute. Well, the address lines on the 2364 ROM, there are 13 of them, and there's one chip select line. So that means you can fit all the address lines on port B because there are 13 5-volt tolerant pins, but you can't fit the chip select line. That has to go somewhere else. That means you need different instructions to load in your address lines and your chip select line. Ideally, you'd load them in together in a single instruction. That would be much more efficient because you typically want both the address lines and the chip select line at the same point in time. I could fit all the data lines on a single port here, but that was also suboptimal because two of the 5-volt tolerant pins on port A are the SWD debug lines. And I really wanted to keep them active during the application because that aids the reflashing and means you can do the in situ reflashing really easily, like I showed on the previous video. Then if we look at where these 5-volt tolerant pins are on port B, they're in suboptimal locations for this application because PB0 and 1 and PB5 are non-5-volt tolerant. So when you read in this 16-bit register, the two least significant bits, bits 0 and 1, are not your address lines, and also bit 5 is not your address line. What I wanted to do in my software was take that entire 16-bit register read and use that as an offset to a RAM address to load the byte to serve on the data lines. The STM32F4 series has quite a small amount of RAM. I think it's 20K for the F103, and I couldn't fit a 16K image in RAM, so I'd have to use that offset of flash. And when you're running at high clock speeds on any of these microcontrollers, you have flash wait state, so that's extra cycles that the CPU is waiting for the flash to respond when it queries information. And things like caches and prefetches don't help you there when you're doing random access of flash memory, so you really want to keep your lookups from RAM if at all possible. So what I had to do was read in a 16-bit register, shift it right 2 bits, and then apply that as an offset. I was still leaving PB5 in, so I didn't have to do any further bit manipulation, so I was using a 16K image rather than an 8K image in RAM to do the offset for. But this was one of the reasons why the performance on the STM32F4 wasn't good enough, that I had to do this bit manipulation. A second was chip select line was on a different port, so I had to do a separate register read for that. And third was just the overall performance of the STM32, the F1. The clock speed was just a bit too slow, and the cache, the prefetch from flash and the caching just wasn't good enough to make this implementation fast enough for ROMs like you find on the Commodore 64. Here we have the STM32F4 schematic, and I haven't bothered labeling which of the GPIOs are 5-volt tolerant because basically they all are. So you'll notice here that I've got all the address lines on port C. The reason why I went with port C over port B was partly because it was easier to route the traces, and partly because there's a few special pins on port B. One of them is boot 1, and I wasn't 100% sure what the state of that pin would do at reset, so I used port C for the address lines. You can see I've got all the address lines and the chip select line on the same port, and I've got them on pins 0 to 13. That means I can take the value that I read and I can use it as an offset into RAM, and it only needs to be a 16K address space. 16K rather than 8K because the chip select line is embedded within that group of address pins. We'll come on to why that is in a moment. And you can see the data lines, I've got those all on port A 0 to 7. I didn't mention this, I forgot on the STM32F1, but I had to go with 8 to 15 because that was the 5-volt tolerant pin. So once I read the byte back from RAM, I had to shift it left 8 bits. It's another instruction, another cycle or two. Whereas here, I read the byte from RAM, I can immediately just write the value to the register, the port A register. Those are the only 8 output pins, so I can just blat the register with the value and none of the other pins are affected. One other thing to note in this schematic is that there's some slightly different pin assignments on the F405 and F415 compared to all of the other F4 variants, and those are the VCAP and VSS pins are slightly tweaked. The schematic here is for revision E, and revision E onwards supports both types of F4 chips. You just have to populate RC4, RC5 and C9 differently depending on which you're using. Haven't yet verified this hardware design though, as of recording this video. If you look at the port B, the image select jumpers are all connected to port B. Now the reason why these are not contiguous, not next to each other, is because I read these at startup and decide which image to preload into RAM, and the startup time is not as time sensitive, not as performance sensitive as the main loop when it's actually serving bytes. So I can do some bit manipulation here, and I allocated these image select jumpers to the particular pins to make routing the PCB easier. When you've got this denser set of traces on such a small PCB and you're trying to hit the cheapest PCB manufacturing options with your trace widths, it's quite hard to fit everything in. You may have noticed that all the address pins are jumbled up, and obviously the chip select line is in the middle of those. You may be thinking, Piers, don't you need to rearrange those before you look up the byte in RAM? Similarly, you may notice that the data pins are the wrong way round, and therefore don't I need to flip the data byte around before I write it to the output register? I don't need to do that because I'm doing as much pre-processing as I possibly can to the ROM images that are going to be served before they get embedded within the STM firmware. So the build process for Software Defined Retro ROM has a stage where it reads in all the different ROMs that you want, whether from local files or download them from zip files and uncompress them. And then it rearranges the addresses that the particular bytes are found at, so that the STM itself can just take this particular ordering of address pins and address the image with that. Similarly, I'm flipping the data bytes around so that they're the right way round for being written by the STM to this output port. Sort of code that takes me quite a while to get my head around and make sure that it's working properly. One of the key philosophies behind this project is you do as much as you can before the fact, so that the number of instructions, the number of cycles that are executed in the main loop is as small as possible to hit the timing requirements. So anything you possibly can do at build time, you do at build time. So all of the manipulation and I call it mangling of the address pins and the data pins is done during the build phase. So the images are pre-mangled, written pre-mangled onto the firmware. And then the particular image that is selected via the select jumpers is selected at boot time, written into RAM, so that then the main loop can access directly into RAM, not into flash, and not risk hitting any flash wait states. I wanted to give you an idea of how densely packed the PCB was with components and with traces. So this is the top of the PCB we're looking at the moment. And we have the 2 rows of 12 pins, giving a total of 24 pins. These are the pins that actually go into your ROM socket. These are your image select jumpers, and there's also a boot 0 jumper for the STM32 here. And then at the bottom, these 5 pins are used for programming the device. And then we've got the STM32, the 64-pin quad flat pack package here, taking up most of the space on the PCB. I could have gone for a BGA part, a ball grid array part, with essentially all the pins laid out as a grid underneath as balls. But A, that's really difficult to hand solder. And B, it would make routing more difficult because I wouldn't have the space under the chip on the top side to route the traces. And remember, I wanted to keep this to a 2-layer PCB. Then the rest of the components here are 0603 passive capacitors and resistors. There's a voltage regulator here, and there's one test pad for checking the clock speed. And if I remove the components, you can see all the traces on the top side. I went with 6mm traces. That's 6 milli-inches, 6/1000ths of an inch, so slightly over 0.1 millimeter wide traces with a 6mm distance between them. That's the minimum trace size and spacing that the cheap PCB manufacturers support with their cheapest options. So if you're getting $5 PCBs from PCBWay or JLC or Siege Studio, then typically 6.6 is their minimum trace size and width. So that's what I've used for all the signal traces here, and I've gone slightly higher for the power traces. Actually, this doesn't look too bad. It's not particularly densely populated with traces. This is the underside, and this is more densely packed with traces, particularly in this middle section here, which is underneath the STM32. So there's not a lot of room left on this PCB for anything else. I have actually squeezed on another couple of header pins to a subsequent revision of this, which I'll talk about in a future video. And I've also managed to use this same microcontroller with a slightly longer PCB to replace the 28C128 EEPROM. At least I've got a hardware design for that done. I've not tested it, I've not received it back from Fab yet, but I'm on the edge of what I can fit on this PCB, both component-wise and trace-wide, at least by putting all the components on one side, making them hand solderable, at least for me. Now onto the bit that I'm probably going to spend least time on in this video, although as a software engineer this is the bit that I find most interesting, and that's the code that actually implements this ROM emulation. If you want to deep dive into the code, then you can find all the code available on GitHub, so download it and trawl through it. But if you take a look at it, then you can find it's very configurable. There's lots of hash define options that allow you to turn on and off various features, and also reconfigure things like the frequency of the STM32F4. You'll find lots of F1 hash defines in here. That's legacy, because where I started with this code was with the F1, but that's no longer really supported. It probably doesn't even build anymore. But the clock frequency is configurable all the way from 16 megahertz up to the maximum for the chip, and you can also enable overclocking if you want to overclock the chip and go above 180 megahertz, say, for the F446. There's various debug options supported, like various levels of logging, and also you can output the clock, the PLL output, in fact, on one of the test pads on the device if you want to see how fast the device is actually running. So really the key steps that this firmware undertakes, first of all, comes out of resets a bunch of stuff. It checks whether it should enter the STM32 bootloader, which is a special option that you can enable for debug purposes. And then it initializes the registers to the values they need and the GPIO registers. Then it preloads the ROM image into RAM, and then it kicks off its main loop. And altogether it takes, without any logging, about 1.5 milliseconds from power, 5-volt power being applied to the board, to it entering the main loop code. If you have logging enabled, regular logging enabled, it increases that to 3 milliseconds. Of that 1.5 milliseconds, I don't know precisely, but I think maybe a couple of hundred microseconds thereabout is actually running my code, and the rest of that time, maybe about a millisecond, is actually the STM32 itself starting up and coming out of reset and starting to run my code. As I've said previously, the actual main loop is implemented in assembly for performance reasons. I really need to minimize the number of instructions and the number of clock cycles. And I also want it to remain deterministic whether or not different compiler versions are used. So that really means not relying on the compiler and actually optimizing the code by hand. Now, some of you might say, yeah, compilers are great though. You can probably trust the compiler to do a better job than you can. I'm not so sure about that. And in any case, I don't want to have varieties in the main loop code based on whether you're using GCC 11, 12, 13, 14 and so on. So everything's hand rolled assembly, and it's in the ROM import source file, and everything's actually implemented as macros, as hash defines, with the instructions defined under the covers. This is to help me actually reason with the code rather than staring at a bunch of assembly, which I'm not hugely familiar with. I have everything defined as hash defined, so I can see logically very clearly what every single step of this code is doing. I spend a lot of time optimizing this code and trying to get the fastest implementation I possibly can. I'm not 100% sure I have the right implementation here though, and I've been playing around with some other main loop implementations to see if those provide better or worse performance, and under what conditions they provide better or worse performance. But this implementation as it stands is good enough to replace PET chips when the system is clocked at just 27. The STM32 is clocked at just 27 megahertz. I've been able to successfully replace ROM chips and the character ROM at that level. And on the C64, I forget the exact values, but the character ROM, the STM has to be clocked at 98 megahertz to get a stable character output, at least on my PAL C64. I expect it will be slightly different on NTSC. That means that for at least my purposes, the F411 processor is good enough. That's got a max clock speed of 100. But you might want to go to a faster processor. The F405 is a great processor. It's got a max clock speed of 168 megahertz, and it's got a much bigger flash as well to store more ROM images on it. And also the F446 clocks up to 180 megahertz, so that might be a good option as well. I've not tested with the F446 yet. I thought we'd finish off by scoping the Retro ROM, and I've currently got it installed in a VIC-20. It's the kernel ROM. I'm using an 84 megahertz F401 processor on this particular board. At the top here we have one of the address lines, that's being driven by the 6502. We have the chip select line here in blue, again that's being driven by the 6502. And the purple line is the data line. So when the blue chip select line goes low, the purple line should be being driven by the Software Defined Retro ROM. At other times, other things on the bus will be driving that data line, like the 6502 and the other ROM chips and the RAM chips. So if we take a snapshot and we can actually look at one of these traces in detail. So here we can see the address line going low, and then about 350 nanoseconds later the chip select line gets driven low, and then these are 100 nanosecond divisions. Within 100 nanoseconds the Software Defined Retro ROM is driving the data bit high. Presumably that's right, the VIC-20 is running, it's not crashing. And if you remember from the datasheet, we have 200 nanoseconds to get the data line to the correct state from the chip select line going low, and we have 450 nanoseconds from the address line showing a particular state. Sadly, it's not very easy with the scope to see just how quickly the Retro ROM would have had the bit ready given the address line being signaled, because it's not actually driving the outputs until the chip select line going low. But clearly on a VIC-20 with an 84 megahertz processor, it's fast enough. I hope you found this technical deep dive into the Software Defined Retro ROM interesting and useful. If you've got any other questions about the Retro ROM, please stick them down in the comments and I'll do my best to answer them. If you want to take a look at the hardware files, the software files, you want to build your own Software Defined Retro ROM, everything's on the GitHub project, which is linked to below in the description. If you did enjoy this video, please do consider sticking around. Till next time, rock on.